And now I'd like to introduce Dr. Matthew Shetrone. He is the Deputy Director of the University of California Observatories, which is Lick Observatory's parent organization. He got his undergraduate degree in astronomy at the University of Texas at Austin, and his PhD in astronomy and astrophysics at UC Santa Cruz. He's used telescopes at McDonald Observatory, Keck Observatory, and of course Lick Observatory. And he also has been at the European Southern Observatory in La Silla, Chile. And we are very happy that he has returned to the University of California to be the Deputy Director of our organization. And with that, Matthew will tell us something about galactic archaeology.
Great. So I want to make sure that I make the point about it's me giving a talk, but I'm giving a talk on behalf of a whole bunch of people. So astronomy, if you forgive the pun, isn't done in a vacuum. So we actually work with students and collaborators from different continents. We use telescopes that are in space and are on the ground in North America and South America. We use telescopes from all over the world. If I can collect some data from it, I will be happy to travel there and get the data, or even better, if they'll just email me the data when I make the request. So what is the connection between archaeology and astronomy? So an archaeologist goes off, and if they work on prehistory, they make a dig and they see a snapshot in time. And maybe if they're doing this dig, they see many layers and they say, oh, well, I don't know what's a million years old and what's 100,000 years old. It's really an effort to separate out all those layers. Astronomy is the same. You have an object and you say, okay, are all of these objects the same age? Are they all moving the same direction? Were they all born together? Are they from different places? So there's a whole bunch of questions. It's sort of the same questions that archaeologists see. They get a snapshot of an instant in time. And they have to disentangle things, separate out different parts and ages, and then they start telling stories. And they say, okay, this came from this age, and this came from this age. These people moved here, and these people moved here, and they died out, or they came in and had a conflict. They tell stories, and then they have a hypothesis. And then they go and make another dig to try to test that hypothesis. That's exactly what we do. We use different words. We have a model. We say, okay, we have a model for how the Milky Way forms. And we say, does that model work? What does it predict? What does it look like? What's the story of that model? And that's what we're really going after. And then at the end, we say, okay, great. Did we learn something from that model? Does it tell us something about our place in the universe, what the future of our place in the universe is? That's what we're really after. Okay, and so what are the key things for us? Well, they're distances. We see a point of light on the horizon. Is it a firefly, real nearby? Is it a car at intermediate distances, or is it a lighthouse very far in the distance? It's hard to tell from just a light on the horizon. So we don't know the distance of these ages. That's another tough one. Are these all the same age, or some different? Are these different than these objects? And then we want to know how things are moving. And when I say space and radial, from spectroscopy, which is what I'm an expert in, you get radial velocity. That's the Doppler shift. That's that sound from a train moving past you. It goes from a high pitch, it's from a high pitch to a low pitch. That's the red shift as it's moving away. And then there's chemistry. And chemistry we get from spectroscopy also. What things are made out of, how much iron is there compared to the hydrogen, how much gold, how much uranium. Okay, and if you only look at a small portion of a picture, you don't get the full picture. So maybe you would understand this thing better if you see the whole, if you had observed more than just this little patch. If you had observed here and here and here, maybe you'd have a better picture of what this thing was. And even if you couldn't roll back in time to see what it used to be, you might be able to conjecture what it is a little better. So we do this through models. And I'm going to play a couple of models that people make of the simulation of the entire universe, or a piece of the universe. And then they make this simulation and they say, oh, this thing at the end of 10 or of 12 billion years kind of looks like the Milky Way. So let's carve out a little piece of it and show it as a movie and say, this might be how the Milky Way forms. So it's not a simulation of the Milky Way, it's just something that kind of ends up looking more or less like the Milky Way. So let's use that as a model for what things might be. So this is what the simulation looks like. And there's this funny Z number here up at the top. This is how astronomers tell time. I don't know how we ended up with Z numbers, but Z of 30 is right about after the Big Bang. And then as it counts down to Z of 3, that will be about where people think most of the Milky Way halo formed. Z of 2 will be about where the disk of the Milky Way formed. Z of 0.5 is when the sun formed. So I will count this down as you see it. You'll see two different versions. This is a face-on version. We'll see an edge-on version. Doesn't look like a Milky Way yet. Things are falling in. Look at this big piece coming in. Things are kind of crashing around. We haven't even gotten to where we think the Milky Way was born. Oh, okay, Milky Way has born. That's the Milky Way. Okay, it doesn't really look Milky Way-like. Wow, what was that big thing that crashed there? And what are some of the, oh, that thing just got ripped apart. Okay, oh, Z of 2 has passed, so the disk should have formed. I don't see a very disky thing. Well, maybe that kind of looks disky, but whoa, what's that big plume there? Z of 1, this is 7 or 8 billion years ago, before the sun formed. Okay, it's starting to look a little more disk-like. There's definitely some weird pulsing. Dark areas are where dust is. So there's some dust lanes there, but they kind of are pulsing. It doesn't really look like a spiral. 0.5, the sun would have formed. All right, things are looking more spirally looking now. Definitely, okay. Now it's starting to really look like a spiral galaxy.Maybe we've got some lanes in here, dust lanes, spiral arms. Okay. So we still haven't gotten, we're still like 2 billion years. 1 billion years ago. So this is where multicellular organisms are just now forming on the Earth. Things are still falling in this simulation. So what should you take from this? Well, things are definitely chaotic. It wasn't a spiral galaxy the whole time, through that whole period of time. It might have ended up as one, but it didn't look like one 7 billion or 8 billion years ago. So as you look back in time, as you look at distant galaxies, you may not expect them to look like the ones today. Okay, so let's look at this from a different angle. Now that you kind of see how it ends, maybe you can look and see different things in the, hello, edge-on version. Try again. There we go. This is the edge-on version. Okay. So it's pretty nice in these simulations. You can kind of change your perspective. Instead of looking at it this way, you just kind of rotate the whole simulation and look at it a different way. So things are falling in. 2. Okay, so in theory, the disk will have formed. And we're hoping that in the end, it'll look like a thin pancake-like disk. It's not very pancake-like. It's quite thick at the moment. It's, okay, Z of 1 would be 8 billion years ago. It's still very splashy. it's starting to, yeah, now see, now you can start to see a little bit disk-like. You can see the edge of the Milky Way with lots of dust in it. But this is the halo. The things are still kind of moving in and out of our halo of our galaxy. Okay, the sun has formed. So somewhere in this thing would be a solar-like star with planets forming. Z of 0.1 coming up, so life would have formed. And things are kind of calming down in this Milky Way. So the early Milky Way is clearly very chaotic, and this one looks very quiescent, very calm, this galaxy. Okay. So what can we use that model from? It's just a model. It comes out of a computer, should you believe it? So this is an image from the Sloan telescopes. These are New Mexico telescopes, and they took images of the sky. And then they removed all the bright stars, and they stitched it all together to see if they could see kind of the background of stars. And they found all of these weird streams. Here's a stream. There's one they call the orphan stream. This one is a big one, kind of extends this way and then is in the southern sky as well. They call that the Sagittarius stream, and they actually found the source of that. There's actually a galaxy that's in the middle of that stream. So there's kind of two arms coming off of that stream. So let's just take one of those streams and see if we can understand what it's all about. So this is a simulation of a galaxy falling in, and this is what happens to it. There's two arms. There's the direction of motion, and there's a leading arm. Things get pulled off of this galaxy as it starts to fall, and it gets what we call tidally stripped. There are tidal forces in gravity that causes the tides on the Earth, right? So what the tides are on the Earth is the moon pulling on the Earth, and it pulls the things that are on the outside easiest. The things that move easiest is water. So water gets pulled by tidal forces. So the tidal forces pull off stuff from this galaxy, pulls off on a leading arm and a trailing arm as it moves in this direction. But what's interesting is it depends on your perspective on the sky. If I rotate this simulation, this is what it looks like. Oops, no, not quite like that. It looks like that. So it's falling in, but it conserves its angular momentum. It stays on a single plane in the sky. It doesn't kind of fall in and change direction. It kind of comes in and makes an orbit. And even that orbit it kind of shifts a little bit. So if we look up in the sky, and I freeze this at the right time, there will be this part of the arm and this part of the arm almost overlapping on the sky as seen from an observer, the yellow dot down there, looking outward. Okay, so we have a tidal arms, leading and trailing, and then the core. And wherever the core went, I've lost the core. It was somewhere in there. So how do we get the data we need? Well, we need a telescope. So the telescope we're going to use is called the Apache Point Telescope, and that's in New Mexico. And we're going to put an instrument there called Apogee. And it's going to observe a ton of stars. It's just going to observe there for stars, and there for stars, and there, and there, and there, and there. And it's going to not cover every place on the sky, but it's going to cover a lot of the sky in a somewhat unbiased way. It's going to obviously not observe the things that are too faint to observe, but it's going to try to observe a lot of things. It's going to get about 100,000 stars. And then we're going to put one at Las Campanas Observatory in Chile, and it's going to be the same instrument, but observed from the south. So there's a whole part of the sky that will be observed from down there. There's some facts and figures for those who are uber nerds about where it's observing. It's observing in the infrared, so that lets you look through dust. So looking through dust means you can observe the center of our galaxy, the outer part, the halo, doesn't matter where, you can get it all. In the optical, you get stopped by dust. Okay, this is what it actually looks like. If you've ever taken an astronomy class, you might have forgotten a lot of it, but hopefully you'll remember "Oh, be a fine girl, kiss me." These are different types of stars. Okay, so they were categorized long time ago, and then they didn't know what the categorizations mean, and so they had A's and B's and all sorts of different things, and then they figured out, oh, this is a temperature sequence. These are hot stars, these are the coolest stars, so the order got all shifted, and so "Oh, be a fine girl, kiss me." So if you see a spectrum of a star and it looks kind of like this, it's a G-type star like the sun. If it has a lot more lines, then it's probably an M-type star, which means it's a little cool star. And if it has almost no lines, then it's probably a hot O-type star. So we can categorize the star. That's its temperature, its mass, things like that. And then taking the details of just one type of star here, we create another type of model. This is the observed spectrum, and this is just a piece of this. So I think we're actually taking a piece that's right in here. It's kind of a small little piece so that you're not overwhelmed with crazy lines. But each of these dips is a spectral fingerprint from something. A molecule or an atom or something is absorbing. And we create a model that has no noise in it. This is what the model looks like, and it's pretty much the same thing. But then what's great about a model is you can pull it apart, you can play with it. Take that same model, remove everything but this molecule called OH. And see, all these features are all the OH. And a little dip here is caused by carbon monoxide. And these big dips over here are caused by iron. And then you can do that with all the other elements, like this giant one right here. Sorry, I can't draw a straight line. This giant one right here, that's caused by aluminum. Okay? So, using that, we can play the strengths of these, and we can adjust the strength of this line until it matches exactly the synthesis. And so the model changes, and that's how we know how much of all these different elements are in a star. I mean, it's a little more complicated than that, but that's basically what we do in spectroscopy to get the chemistry of a star. Okay, so we observe, we are here, and then this is where we observe. So we don't observe everywhere, but we observe a lot of places. This is from the northern observatory, and then of course the south points out all these directions that we can't observe in the north. There's some overlap. They can both observe in kind of these directions. But this is just to let you know that it's not a perfect survey, but it's as good as you can do in 4 years of work. But that's not all we need. It's not just spectroscopy. Remember, spectroscopy is the chemistry. Spectroscopy is the radial velocity, but we don't know anything about how it's moving like this on the sky, the plane of motion. So to get that plane of motion, we have another thing called Gaia. This was launched by the Europeans. It's a spacecraft. It's going to observe all of these stars in the Milky Way. And so it doesn't quite reach the center of the galaxy, but for all of these stars, it can measure how things move like this on the sky. And it does that by taking an image now, and then it looks a year later, and then it looks a year later, and it looks at little tiny motions of those stars and says, is it moving fast? Is it moving north, south, east, west on the sky? And it makes a catalog of millions of stars. So we combine that millions of star motions with our hundreds of thousands of chemistry and velocities this way, and suddenly we have this huge database of chemistry and total space motion. Okay, so this is just explaining the reach. Before Gaia, this was as far as we could reach to understand space motions. And then they launched this satellite, and this is how far we can reach. So it's done tremendously better. Okay, and it found a bunch of streams on its own. all of these different things, and each of them seem to be associated with a cluster. So this is, if you're an astronomy nerd, there's a cluster called M30, and then there's a stream that belongs to M30. And 362, there's a stream that belongs to it. And so we find lots of streams that Gaia is finding. So Gaia is saying, look, when you have a cluster, the cluster gets pulled apart, and there are little streams. So it's kind of like our movie. Okay, and so this is just to remind you what we're looking for. We play my little movie. Is that when we look out from our galaxy at Sagittarius, this galaxy that's falling into ours, we see overlapping pieces. Some of it's going to be the leading arm as it gets pulled apart. Some of it's the trailing arm, and they overlap on the sky. So it's very complicated to tie this apart unless you've got the total space motion. And so this is what the actual data looks like. So we've got the core of the galaxy, and then we can map out the leading arm and the trailing arm. I might have those backwards. So, but we can tie back. Sometimes we get our guesses are wrong, and these are stars that are not in either one. But we do okay, and we can sort of say, okay, we found a whole bunch of stars that seem to be part of Sagittarius's trailing arm and leading arm with the motions. Is there any chemistry difference between those two? We're going to go a little deep, but here it is. So Sagittarius, this axis, this is the amount of iron. Fe is the periodic table for iron. This is on a log scale, so solar would be here, 10 times less than solar would be here, 100 times less than solar would be over here. So the Sagittarius spiral are the yellow. This is a histogram. So most of the Sagittarius core is sort of a little bit less than the sun in the amount of iron it has, those stars. If we look at the trailing arm, it's a little different than the Sagittarius galaxy itself. And if we look at the leading arm, it's really different than those two. So there's some distribution difference. There's overlap, sure, but there's some distribution difference between the two. So what does that story mean? Well, the way we interpret this is that galaxies are like onions. And so the first stars that are born are a shell or a group. And then you lose a little bit of angular momentum, and because you make a generation is by blowing up, and then gas has to come back together to form the next generation. So stars start to collapse, and the gas cloud collapses. So the next generation's a little bit smaller, and the next generation's a little bit smaller, the next generation's a little bit smaller. So each generation is more chemically advanced. You start with the Big Bang, all hydrogen and helium, stars blow up. The first generation has, or the second generation has hydrogen, helium, plus the remains of that first generation. So a little bit of iron. Those stars blow up into a gas cloud. That gas cloud forms stars. That's the third generation. It has even more iron than that generation. So each generation has a little more iron, a little more iron, a little more iron. So the onion falls towards the Milky Way, begins to get tidally stripped. What gets tidally stripped? The stuff that's the easiest to pull off, the outer part. So the leading arm is stripped, and that's the least chemically evolved. And then the trailing arm, the next onion in gets pulled off, or the next layer in gets pulled off, and it's the next least chemically evolved. And then the stuff that remains is the most chemically evolved. It's the center of the onion. It's the most chemically complex. Most number of generations went into it. So it starts to form kind of a good picture that is consistent with that model of stuff falling in and getting ripped apart and forming the Milky Way. But that's the halo of our galaxy. But there's more than just the halo, there's the disk. The disk of our galaxy has chemistry as well, and the chemistry in the center of our galaxy, this is the center, this is, and then this is 5,000 parsecs out, 10,000 parsecs, and this is sort of the edge, 20,000 parsecs. The sun is at about 8. Okay, so the center of our galaxy, lots of stars, and is very chemically complex. The outer part of our galaxy, a lot less stars, and is least chemically complex. Fewer generations are going into it. But you still find young stars there, stars being formed, but they're less chemically complex. There is one interesting thing here. If you take, instead of just looking at the average or median value where you're just talking about this, but if you actually make a cut through here, you can sort of see there's an asymmetry. These are contours. The contours are stretched one direction over here, and they're kind of stretched a different direction over here. It's a little hard to see, so I will make cuts like this and plot them. And this is what they look like. So this is the yellow are the ones in the outer galaxy. The average is over here at a minus value, so not very chemically evolved. And you notice there's kind of a long arm that stretches out this direction. The center, or more center part of our galaxy, is more chemically evolved even than the sun, but it has an arm that stretches the opposite direction. You call that skew, and the skew is different for different parts of the galaxy. And so we've thought about this, and I had a student who came up with a clever model, 2 models actually, to test and say, how does this happen? And there are 2 ways to think about this. One is salmon, and the other is bald eagles. And salmon are born in a river, and then they swim out to the ocean, spend some time there, then they go back to the same river, and so they kind of move back and forth. So a snapshot of where they're born is one location, and then it kind of spreads out a little bit, but it is limited, it's finite, it doesn't go very far, and they go back to the same location. And so that's this kind of model. They're born in one location, and then it kind of spreads out a little bit, but you don't get a huge, you get a little bit of distance, you get some distance away, but it kind of is limited. The other one is bald eagles. So in a bald eagle, you look at a baby bald eagle. If I went outside and found a baby bald eagle and say, where's that bald eagle from? Well, I know where it's from. It's only 1 month old. It's from here. But if I see an adult bald eagle and it's 5 years old, I don't know where it's from. It could be from Seattle. It could be from the Sierra Nevadas. It could have moved here permanently, and I don't know. So that's a different thing. That's an emigration. That's a permanent migration as opposed to an annual migration. So in that, stars are formed at one location and then they permanently go someplace else. And why would they go someplace else? If you take a star and it's going around like a record player on a record, but it doesn't. It comes in contact with other things. There's another star that it comes past. And it goes, oh, I got kind of close, and so it influenced my orbit. And then there's a big group of stars, a cluster, and it goes past that cluster and says, oh, that was a big kick I felt, and so I'm going to change my orbit a little bit. And it might pass a gas cloud. And so each time it interacts with something in its orbit, it changes its orbit permanently. So of these 2, the one that matches the data better is this one that's called churning. It's the one that's emigration. It seems like stars don't do like salmon. They don't go from one place to another place and then back and forth and back and forth. They move permanently, not all of them, but some of them move permanently to a new location from where they're born. So that gives us a picture of the Milky Way as a dynamic place. Things aren't born and stay there and go around like a record on a record player. They're moving. Okay, so if that's true, then the inner part of our galaxy is chemically evolved. The outer part is less chemically evolved. If you look at young stars, I had another student who just said, okay, let's separate out young stars from old stars and see if there's any difference in their chemistry by age. So he said, oh, look how steep this is. The inner part of the galaxy has very chemically evolved stars. The outer part has less chemically evolved. It's a pretty clear trend. But for old stars, it's less clear. Why would that be? Well, once this star is born and is given some amount of time, let's say it's given 1 billion years, it could move from here to here in distance. And then it's given another 1 billion years, and it can move from here to here, and then here to here. Or over 4 or 5 billion years, some of the stars could move over here, which smears out, which means this distribution won't be just here. It won't be just these stars that were born locally. There will be some stars that had moved from here to here, which spreads out the distribution. So we're seeing evidence that stars migrate. Okay, so what does that mean? What does it come back to? That the outer part of our galaxy is metal poor. The inner part of our galaxy is metal rich. Okay, great. Who cares? What does that mean? What does that matter? Well, you need metals to form life. We're made from carbon, we're made from iron. The center of the Earth has uranium in it that heats up the core of the Earth, which creates a magnetic field which protects this planet. If you had less metals, it might be harder to form life. It might be harder to heat up the core of a planet to create that magnetic field. So it may be that the outer part of a galaxy is a hard place to make life. The inner part of a galaxy might be easier, but then the inner part of the galaxy also has a lot more stars. So there's a lot of weird stuff that goes on, explosions. Stars get closer together. They could interact. Okay, you can find young stars all over the galaxy, in the inner part and the outer part. And stars seem to migrate. So 5,000 parsecs would be an okay thing to see a star migrate. Where was the sun born? We're in this Milky Way, right? If we go out and look at all the stars around us, is the chemistry of all the surrounding stars typical of the sun? It's not. So if we do an analysis, this is still very controversial, and there's debate about this in the literature, but it looks like our sun may have moved about 2,000 parsecs. We're at 8 kiloparsecs from the center. It seems like maybe we were born at about 6, and our sun emigrated out 2,000 parsecs over its lifetime so far. It's moving out to the suburbs. So the Milky Way is a dynamic place. So what I'm hoping that you've learned is that things are very dynamic in the Milky Way. They run into each other, things are falling in, they blow up. It's over long time scales, sure, but if you look through a telescope, if you see a picture of something in deep space, it's a snapshot. And so you have to say there's a story behind that snapshot. Maybe you see an old cluster. What has happened to that old cluster? Was that old cluster always like that, or has it been stripped off, some of it? Okay, and the inner part of the galaxy is a very busy, dynamic place. Maybe it's not good for forming life because it's got a big black hole at the center that could cause radiation out and be very dangerous to life forms forming there. The outer part evolves more slowly, it's more metal poor, so maybe the outer part of the galaxy is a tough place to form life. Maybe we're the Goldilocks zone of our Milky Way. Astronomers like archaeologists are trying to roll back the clock. We see a snapshot and we're trying to understand the past from that snapshot. We use models to predict the future. And we use that model to say what's right and what's accurate and what's not accurate. We are not in the truth business. All we're in the business of is finding better models. Newton had a theory of gravity. It works really well. Okay? For a long time, for hundreds of years, people thought that's it, gravity's been solved. And Einstein came along and said, well, what about the orbit of Mercury? The orbit of Mercury doesn't match Newton's gravity law very well. What about stars, passing a massive object? That doesn't seem to match Newton's gravity very well. So Einstein came up with a new theory of gravity, or a new model for gravity called general relativity. We've tested it, it works better. So we drop the old Newtonian gravity model, unless we really need it for something, as a simplification, and we say we have a better model now. Is Einstein's model right? Maybe not, but it's a better predictor, and it's the one we have right now. That's what we're doing, is we're just making better and better models. Okay, so speaking of models, let's go back to this one last time. And now that you know what we're looking for, streams, things falling in, emigration of stars, maybe you'll see this simulation in a slightly different way. Whoops, wrong one. Come on. Okay. Things are falling in. The Milky Way, quote unquote, when people say the Milky Way is about 11.5 billion years, hasn't even formed yet, but look, there's something there. Now we say it has formed. Things are falling in. It doesn't look very spiral galaxy-like. So if you were to look at a most distant galaxies, this might be more like what you see, that eventually becomes a spiral, but doesn't look like it in very distant galaxies. Okay, the disk should have formed by now. Look at these plumes. Things are falling in, causing disruptions. That's probably an explosion or an AGN going off, moving the dust lanes around, pulsing. Okay, the sun forms at about 5 billion years, 0.5 here is 5 billion years. Okay. Maybe we were really lucky to have formed in something that is much more stable than in the early times of our Milky Way, where things were much more chaotic. And remember, this is just a simulation that kind of ends up looking mostly Milky Way-like. This isn't trying to replicate the Milky Way. Okay. So, this is one of the images we started with. Remember, you need to see the big picture. If you just have a little tiny piece of the picture, you may not get it right. You may not understand what you're looking at, and you may not be able to figure out a model that allows you to roll it back and see what it is. This is my little rollback. So I hope you can take this and put it in context of what you see through the telescopes, and say, what is it, or the next time you see a picture from the JWST, which is now going to be producing pictures, when they show pictures of distant galaxies, and you see they all kind of look torn up. early Milky Way looked very torn up in its early days. And then it evolved and became more regularized. But I want to give you lots of time to ask questions, so I'll end there. Thank you. Any questions?
Why do galaxies tend to be in a plane, not a sphere?
So some of them are in a sphere. So there are two. Back when they first started stamp collecting galaxies, and they started saying, oh, let's make the galaxies into different groups. And these look like spirals, and their spirals are kind of flat, and they rotate. And these are what we call ellipticals, and they don't rotate very much, and they're not flat, they're more round. So there's a class of galaxies called elliptical galaxies. And we now understand that elliptical galaxies are probably spiral-like things. They were spiral, and then you had something big instead of something small that kind of makes a little small disruption. Something that comes in that's big erases almost all that angular momentum, and then it becomes just kind of a mess, a spherical mess. So, other questions? Yeah, go ahead.
In the beginning of in your model, you were saying that things are falling in. Were these like clusters falling in together, forming that initial phase when the galaxy is being formed, or what was it?
Right, so some of those would be small enough to be called clusters. Some of them would be what's called dwarf galaxies, and some of them are bigger. So, and that process continues, right? Right to the end, there was still stuff falling in. And right now, there's this thing called Sagittarius, which we see as a core. That's a Sagittarius dwarf galaxy. So it's maybe 100 times smaller than the mass of the Milky Way. And it's falling in right now, getting torn apart. What's more interesting is in about 1 billion years, depending on how we believe the velocities, Andromeda, which is our sister spiral galaxy, which is really our big sister. She's about 50% bigger than we are. And the Milky Way are going to pass across each other. And because we're the little guy in that, we're probably going to be the one torn apart. So it won't affect our solar system, but it might affect our beautiful galaxy. Will probably no longer look like a beautiful spiral. It'll go and it'll look very irregular or spherical after that event. But there's a lot of space between stars, and so the stars are unlikely to run into each other. Okay. Anybody else have a question? Go ahead.
Another one. So why is it that iron and metal form in the older, or the newer stars? Why does it tend to go in that direction?
So the center of a star is a fusion engine. And so fusion is the process, and hydrogen is the first fuel. And so it takes all the hydrogen atoms, pushes them together, and makes helium. And then when it runs out of hydrogen, it says, okay, if I have enough mass, I'm going to make fusion from helium. It takes 2 heliums together and makes a carbon and nitrogen or oxygen. And then it runs out of helium in the center of the star, and it keeps doing that and keeps doing that and keeps doing that until it gets to iron. And then at iron, it sort of says, oh, I'll just take 2 iron atoms and start pushing them together. But quantum mechanics says, once you put 2 iron atoms together, you lose energy, you don't gain energy. And so the whole thing collapses, and you get a supernova, and the star rips itself apart. And so if it successfully rips itself apart, then it feeds the next generation a whole bunch of iron that it made. And in the process of blowing up, it can remove some of that energy and make things that are heavier than iron, like gold and uranium and things like that. Go ahead.
How do you tell stellar emigration
Uh-huh.
from depleted
So through tagging. So we take all the stars we find and we look at their spectrum and we say, this one has this much iron. Let's find all the stars that have that much iron and say they're a generation. And then you can look at their motions. And you say, of all those that are a generation, which ones formed together, maybe in a cluster? So if you see the Pleiades, it's kind of a beautiful cluster of stars. All of them are forming together. In space, they're all kind of moving together like this. So even if they drift apart slowly, they're still kind of moving in the same direction. And so you can take chemistry plus motion and tag the stars and roll the clock back and say, these guys all belong together. Slowly, it gets harder and harder. If a star has a little interaction and gets kicked out a little bit, its motion becomes less reliable for rolling the clock back. So the older something is, the less you can use its position and motion to roll back the clock, because you can't undo all of those little random kicks that it gets. So it gets hard, but you still have the chemistry. So if you see something unique in the chemistry, like, look, this star has a lot of weird lithium. Oh, this one over here also has weird lithium. Maybe they were born together. So there's still that chemistry tagging you can do. I hope that answers your question. Okay. Anybody else? No? Oh, yeah.
So you mentioned that it took 4 years for that program where Apogee was running on the northern and southern hemisphere.
Uh-huh.
Is that time because of the like you have to observe the motion of the stars, and you were not able to perceive it in shorter time frames, or is it limitation of processing, like because it takes a long time to process the information that you gather, or is it just a matter of it just takes a long time to gather it?
It takes a long time to gather information. I wish that the answer weren't more banal. The real answer is we have a limited amount of money for that experiment. And at 4 years, that was the end of the money. And so that instrument still exists, but there were some other people who had other ideas and they had other money. And so they've built together and said, we're going to do a slightly different experiment and do something. And so I don't happen to be part of that experiment, so they've gone off to do something new, and I'm still digging, rummaging around this old data set to see what I can squeeze out of it. So, but there are new generations of astronomers who are jumping in and saying, this is going to be cool. And they started in December with this new experiment. And it's going to be 3 years that they have funding for, and they're going to get through that in 3 years. So, but it's 3 dedicated years of people plugging or moving fibers around on the sky and observing and then taking that data set, and it's going to be terabytes of data for them to process. So for our experiment, it took 4 years to collect the data. It took 3 months to get the final analysis of a computer, as a supercomputer, sitting there for 3 months, putting it all together. And we're still writing papers, and probably will write papers for the next 2 years, just based on that data. So in a period of big data, the limiting power is how fast you can think about the big data. Anybody else? Okay, well, thank you for all coming, and I hope you enjoyed your view through the telescope and the science lecture, which puts perspective on that viewing through the telescope, and enjoyed the music.